Hello! In this video we're going to be graphing exponential growth and decay. This is all part of our new unit on special graphs and functions. So in this video we're going to be specifically dealing with graphing exponential functions. So we're going to look at graphing exponential growth versus decay. My goal for us today is very simple. I just want you to be able to identify what the picture looks like when it looks like growth and when it looks like decay. I also want you to be able to take a look at an equation and be able to tell me whether it's growth or decay. We're going to get into more specifics in the videos that follow. So today let's keep it simple. Let's look at exponential functions in general and what they look like. A function, as you recall, is a rule that shows a relationship between the input and the output, where there is only one output for every input. That means you put one thing in, you get one thing out. Now, this is your formula for exponential growth, and what you're going to notice is x is your variable, and that is your exponent. That's what makes this very special and very different when we graph it. So you will notice, to be growth, a must be larger than 0. In other words, you know if it's less than 0, this is going to be flipped and be reflected so that it's down in the negative region. So to be growth, we need this to be up in the positive. And we need our b to be greater than 1. So this is going to be our ratio here. So let's take a look at our first example. So our function rule is y equals 2 to the x power. So all of my domain values are going to go in for x. That's our exponent right there. I've also asked you to do something called restricting the domain. Now, I've never asked you to do this before, and basically what that means is we are only going to graph between -2 and +2 inclusive. So let's input our values here. So this would be 2 to the -2nd power. And if you remember what negative exponents mean, they actually mean reciprocal. So that's 1 over 2 squared, which is 1/4. 2 to the -1st power means 2, whoops, let me fix this here, means 1 over 2 to the 1st, which would be a half. 2 to the 0 power, well, anything to the 0 power is 1, except for 0 to 0, that's undefined. 2 to the 1st power is 2. 2 to the 2nd power is actually 4. Now, just so that you see this pattern here, moving up, if you notice, everything doubles. In other words, if you double 1/4, double that, you get 2/4, that's a half. Double 1/2, you get 1. Double 1, you get 2. Double 2, you get 4. So that means 2 to the 3rd power would be 8. 4 doubled is 8. 2 to the 4th power would be 16, because you would double it. Now going the other direction, you would actually be taking half. Now hopefully this makes sense that when we move this way on the graph, we are doubling, because look at what your b or your base is. It's 2. That would mean you're doubling. If it were 3, you'd be tripling. If it were 4, you'd be quadrupling. The other thing that I want you to notice is the relationship between the negative and positive exponents. So where 2 to the +3rd power right here is 8, if I had given you, if we had continued going the other direction, if this were a -3 here, that would be 2 to the -3rd power. That would actually be 1/8. And if I were to continue this on and go 2 to the -4th power, that would be 1/16. So you'll notice the relationship between these values here and these values here is that they're reciprocals of each other. Okay, let's graph this on our graph here. So an input of -2 is 1/4. An input of -1 is 1/2. An input of 0 gives me an output of 1. An input of 1 gives me an output of 4. and an input of 2. Whoops, there's my 2, there's my 4. Let me fix that. So if I connect my dots here, this is going to be a curve. That's what it would look like. Now, just so that you know, exponential growth, if I were to look at the entire graph, would look something like this. And it would go on for infinity, and here it would get very, very close to 0. If you think about going this direction, we have 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, 1 over 128. If we were to keep going with that pattern, the denominator would get infinitely large, which means that the value of the fraction would get infinitely small, but never be 0. Let's take a look at that on our graphing calculator. Okay, so here's our graphing calculator. I've graphed the function, and what you will notice, and I'm going to zoom out here. So I'm just going to go to Windows Zoom, and I'm just going to do a standard zoom out. Okay, and the other thing that I can do is I can actually trace. So I'm going to trace this, and you will be able to see as I move one direction, this is going to grow really fast. But if I go the other direction, you'll see my input and output down here. So this would mean I'm inputting negative 1.5 and I'm getting an output of 0.354. And that very well could be a rounded answer. Notice I'm continuing to get smaller, smaller. I'm not touching 0, but it looks like I'm touching 0. You'll notice the E here. That stands for scientific notation. And it's going to continue to get smaller and smaller. You'll notice our scientific notation. This means 5.39 times 10 to the negative 6th power. That means you'd move the decimal over 6 times in the negative direction. Hopefully you remember that. So that's times 10 to the negative 6. It moves this decimal 6 times this way. I can just keep tracing, and this is just going to get smaller, 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 and smaller. But it's never ever going to be 0. Okay, it's an interesting thing. So this is growing. If you move on your graph, when we read a graph, we actually go left to right. So if you look at this, this is always going to be increasing, always increasing here. And that's why it's exponential growth. So let's take a look at another question here. Okay, with this question, it's just the reverse, and this is decay. So this one would be exponential decay. In this case, we still have an a value that is bigger than 0 because we don't want this thing reflected down in this region right here. That's not what we want. Okay, and our b value has to be between 0 and 1. Okay, again, I'm restricting the domain between negative 2 and 2. So 1/2 to the negative 2nd would be, if you remember, this means reciprocal. So I'm going to do 2 over 1 and square it. That's 4. 1/2 to the negative 1st power, we are going to flip it. So it's 2 over 1 to the 1st. So that's going to be 2. This is going to be 1/2 to the 0 power, which anything to the 0 power except for 0 to 0 is 1. 1/2 to the 1st power is 1/2. 1/2 to the 2nd power is 1/4. You will notice between this and the graph that we just did, it's going to be the reverse. So if you notice, the values for your output are actually just reversed. Okay? So if I graph this, negative 2 has an output of 4, negative 1 has an output of 2, 0 has an output of 1, 1 has an output of 1/2, and then this would be 1/4, and so on. So if you notice, we're continuing to take, whoops, why are my dots moving there? Okay, we're continuing to take half each time. So let me connect my dots. So whatever this is, it's decaying at a rate of 50% or 1/2. So we have something that's decaying or wearing away. And if I were to look at the entire graph, it would look like this, and it would get really close to this axis but never touch zero. So this is a case of something that's actually wearing away, and this one is always decreasing. Now let's see if you can recognize when something is growth versus when it is decay. In this one, my base is actually bigger than 1. Because it's bigger than 1, this would be growth. Now I'm going to look at my base here. This one has a base that is less than 1, so it's between 0 and 1. This would be decay. And what this actually means, right here in this, in this one right here, is that 20% remains each time. And that's going to make more sense to you when we start talking about real life growth and decay. But this means that something's wearing away at a rate of 80% and 20% actually remains. If we take a look at this one, this is between 0 and 1. This would mean it is decay. What this means is that 2/3 remains each time and 1/3 actually wears away. So 1/3 wears away, 2/3 remains. This one is considered growth. So what this means is this is going to get 4 times as large each time. So it actually increases by 300%. Okay, so if the base is bigger than 1, it's growth. If the base is less than 1, it's decay. So big thing to remember, if this number right here is bigger than 1, it's growth. If this number right here is less than 1, it's decay. Okay, let's take a look at this one. It's a 3, so is this growth or decay? Hopefully you're looking at the same growth because it's bigger than 1. So we're going to do 3 to the negative second, which means 1 over 3 squared, which is a 9th. We're going to do 3 to the negative first power, which means 1 over 3 to the first, which is 1/3. 3 to the 0 power is 1. 3 to the first power is 3. 3 to the second power is 9. So you will notice as we move this way, we are tripling. These are getting 3 times as large. So 3 times as large. With linear, we would be adding or subtracting, but with exponential, we're multiplying here. All right, so -2 has an output of 1/9. It's very tight here. -1 is 1/3. 0, 1. 1 has an output of 3, and 2 has an output of 9 that just squeaks in here. So I'm going to graph this, smooth graph here, and clearly you could see that as we read a graph from left to right, this thing is growing. It's, whoops, stay there, buddy. This thing is growing. Okay, let's take a look at another one. All right, we have 1/4 here. That is less than 1, so this should be decay, meaning that something is wearing away here. So we have 1/4 to the negative second, which means flip, and square it, so this should be 16. That's 1/4 to the negative first power, which means 4 over 1, which is just 4. 1/4 to the 0 power is 1. 1/4 to the first power is just 1/4. And 1/4 squared is 1/16. So you can see as we're moving down here, a fourth remains each time. So 1/4 remains each time. Okay, so we're taking a fourth each time. So let's see, -2. Output is 16, so that's going to be way up here. -1 has an output of 4. 0, 1, 1, 1/4, and 2 is 1/16. Boy, that looks really close to the axis, but you know it's not going to touch it. And now I'm going to do a nice smooth curve the best I can, and there you go. It's not pretty. Now, because we restricted the domain, we're not putting arrows on it. And let's try one last one here. This is going to be 6 times 2/3 to the x power. So this is kind of an interesting one. So we're going to do 6 times 2/3 to the -2nd. So that's 6 times, let's see, let's flip this and square it. Flip it and square it. So that would be 9/4. So let's see, 2 goes in there twice, 2 goes in there 3 times, so that's 3 times 9 divided by 2. So that's going to be 27 halves. Whoops, stay right there with me. And that's going to be, what is it, 13.5. Continuing on, 6 times 2/3 to the -1st would be 6/1 times 3/2. 2 goes in there once, 2 goes in there 3 times, so this gives you 9. 6 times 2/3 to the 0 power would be 6 times 1, which is 6. 6 times 2/3 to the 1st power. Let's see, 3 goes in there once, 3 goes in there twice. This is going to give you an output of 4. 6 times 2/3 squared would be 6 times 4/9. So 3 goes in there 3 times. 3 is going to go in there 2 times. 2 times 4, so that's going to be 8/3. And 8/3, if you wanted to change it to a decimal, would be 2.6 with the bar over it. So I'm going to go ahead and graph this. -2 would be 13.5, so that's up here somewhere. -1 is 9. 0 is 6. 1 is going to be 4. And 2 is going to be 2.6. So somewhere around there. Okay, I'm going to connect my dots here. And I want to make one more connection with you. And that connection is, you'll notice that I did not put any plus or minus with any of these, like +5. That would bump this whole picture up 5. Hopefully you knew that. Now, as long as I don't have any pluses or minuses on there, you will notice something about this number 6. It's where it crosses the y-axis. Interesting. Let's take a look. Does that hold true? So the leading coefficient on here would have been 1. Notice this crosses right here at 1. My a value would be 1, because remember our formula is y is equal to a times b to the x. So if you don't see a number here, it's 1. Notice this crossed at 1. And if I go back to these, that would be 1 times 2. That would be 1 times 2 to the x. Again, it crosses at 1. So that's going to be very important for our next lesson. So I just wanted to draw your attention to that. What I'd like you to do is I'd like you to do a few practice questions. There aren't many of them, but what I would ask that you do is you do it on, you can do it on one piece of graph paper. Just draw one big chart, and you may need to go as high as maybe 20. You may have to go as low as 20 on the y-axis. You don't have to go as wide on the x-axis, but you do on the y-axis. So what I would suggest doing is taking one piece of graph paper, doing all your questions just on that one piece of graph paper. You can always use your input to get your input-output table. You could always go to your graphing calculator. That's certainly acceptable. I did it by hand because I thought it was easy enough, but you don't have to. You can use your graphing calculator to do your input-output. Check your answers with mine, and we'll see how we do. All right, good luck everyone.